Section 10.1 deals with the chemistry of carbon, so getting started here in organic chemistry. And the first question we want to address is, why are there so many organic compounds? If you think back to general chemistry, which is a prerequisite for organic chemistry, in general chemistry you spend a lot of time talking about many elements in the periodic table. In fact, you practically discuss the entire periodic table. Whereas in organic chemistry, we focus almost exclusively on compounds that contain one element, and that element is carbon. So we're concerned with compounds that contain carbon. And we're going to spend an entire semester just discussing compounds that contain carbon. And the reason why is because there are so many organic compounds, or compounds that contain carbon. And now we're going to address the question as to why are there so many of these organic compounds, these compounds that contain carbon. The first reason is that carbon forms stable covalent bonds with other carbon atoms. So if you think about an element like sodium, which you would have discussed quite a bit in general chemistry, sodium doesn't form bonds with other sodium atoms, but carbon does form bonds with other carbon atoms. And carbon can even form up to 4 covalent bonds with other carbon atoms. So a carbon atom can be bound to another carbon atom like this, and then I can add another carbon. Of course, none of these carbons have a complete octet, but the idea is that carbons can be connected to each other. The second reason is that carbon atoms form stable bonds with other elements, such as oxygen, nitrogen, sulfur, the halogens like chlorine, fluorine, bromine, iodine. Those are the halogens. It can also form bonds with elements like silicon and phosphorus. So carbon can form stable covalent bonds with many other elements. And it says here in the last bullet point that the presence of these other elements confers many new physical and chemical properties on an organic compound. So what you're going to see is that these elements that are listed here and others can provide organic compounds with unique physical and chemical properties. The third reason is that a carbon atom can form a double or a triple bond with another atom or with another carbon atom to produce a variety of structures with differing properties. For example, if you take a look at this compound shown right here, you can see that the carbons, they have a double bond between the two carbon atoms. But you can see that there's a double bond between this carbon and this oxygen up here. So carbon can form a double bond with another carbon atom, and it can also form a double bond with an oxygen. It can also form double bonds with other elements, but these are just two specific examples. And also, carbon atoms can form triple bonds. So not only can they form triple bonds with each other, so you see two carbon atoms here in a triple bond, they can form triple bonds with other elements like this nitrogen that's shown here. So we have 1, 2, 3, so there's our triple bond. And something else that you might have noticed is that carbon always forms 4 bonds. So you see this carbon that I have highlighted in blue down here, you can see that it forms 1, 2, 3, 4 bonds. If you look at this carbon over here, you can see it has 1, 2, 3, 4 bonds. So carbon is always going to form 4 bonds. But again, carbon can form single bonds, double bonds, and triple bonds. And that's another reason why there are so many organic compounds. The fourth reason, it says here the number of ways to arrange carbon and other atoms is nearly limitless. So not only can carbon containing compounds form branched chains, and we'll look at examples of that, it can also form ring structures. So you see, if you look down here, you have all these CH2s and they're together in this kind of five-sided ring down here that kind of looks like a pentagon. And it can also form compounds that have linear chains. So if you look at this compound down here, this molecule, it kind of looks, like it's straight, like a chain, like all these, carbon atoms are linked together. You see we have CH3, then CH2, 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 CH3. So that, we call that a linear chain. It says here 2 organic compounds may even have the same number and same kinds of atoms, but completely different structures and thus different properties. And these are called isomers. So what this point is saying here is that you can have 2 organic compounds with the same molecular formula, meaning the same number of carbons, same number of hydrogens, but the way that the atoms are connected together are going to result in different compounds, that are going to have different properties. So when it says different properties, that means they would have different boiling points and melting points, different densities, and we call these isomers. And we'll look at examples of isomers. An important difference that you have to understand between organic and inorganic compounds is the bond type. So it says here bond type. Now, organic compounds are formed from covalent bonds. And you remember from general chemistry that a covalent bond is one that is a result of electron sharing. So we have atoms that are sharing electrons. Whereas inorganic compounds, and if you're wondering, well, what's an inorganic compound? Those would be things like, sodium chloride, magnesium, let's say magnesium bromide, etc. I mean, we could do this all day, but inorganic compounds usually have ionic bonds, and that is a result of electron transfer. Say, for example, in sodium chloride, the sodium gives up an electron to the chlorine to become a sodium ion, an Na plus ion, and then we have the chloride ion, which is negatively charged. That's inorganic compound. But again, organic compounds are formed from covalent bonds, which are a result of electron sharing. The structural differences between organic and inorganic compounds are shown on this slide. Now, organic compounds, we think of those as molecules, and organic compounds or organic molecules are also non-electrolytes. So if we think about an organic compound, in fact, the simplest organic compound is called methane, and we'll discuss that more later. And methane is made from one carbon atom and 4 hydrogen atoms. Now, if I draw the Lewis structure of methane, it's CH4, so I have a single bond between the carbon and each one of those hydrogen atoms. So this is a molecule. It's held together by covalent bonds, and it is a non-electrolyte. And a non-electrolyte, what that means is that it will not break apart into ions when put in an aqueous environment. Now, inorganic compounds, we don't think of inorganic compounds as being molecules. We think of them as three-dimensional crystal structures. Say, for example, if I have sodium chloride, everybody's favorite inorganic compound, we don't call sodium chloride a molecule. Sodium chloride is an ionic compound. It's an inorganic compound, and it exists in a three-dimensional structure. In fact, you may have seen, the cubic structure of sodium chloride in general chemistry, and you discussed, well, I have the sodium ion and the chloride ion, and then they form this cubic shape, right? And they pack together in sort of this crystal structure. So that's how we view the structure of inorganic compounds. They are three-dimensional. And inorganic compounds are often water-soluble, and they will often dissociate into their ions, meaning that they are electrolytes. In fact, that's the definition of what an electrolyte is. It's a compound that will dissociate into its ions in water. Physical differences between organic and inorganic compounds. First, let's take a look at melting points and boiling points. Now, organic compounds have low melting points, generally speaking, and the reason why is related to intermolecular forces. And intermolecular forces are the forces that hold individual molecules together. And what we're going to see as the course progresses is that the intermolecular forces, or those forces in between molecules of organic compounds, are rather weak and are broken fairly easily. And thus, it's going to be easier to take a solid organic compound and melt it, right? Convert it into the liquid phase, because breaking those forces doesn't take a lot of energy, whereas inorganic compounds are going to have high melting points, and that's because ionic bonds are very strong, very difficult to break, right? Ionic bonds are electrostatic forces between positively charged ions, cations, and negatively charged ions, anions. So again, organic compounds will have lower melting points and boiling points, and inorganic compounds will usually have higher melting points and boiling points. And again, this is related to intermolecular forces. In terms of water solubility, this one you kind of have to take with a grain of salt, because there are several exceptions to this, but I'll just say here, generally speaking, organic compounds, especially what we call hydrocarbons. And the hydrocarbons are compounds that are made only from carbon and hydrogen. These compounds are nonpolar and water insoluble. So if you think of something like gasoline is something that most people are familiar with, and it is a hydrocarbon, meaning it's made from only carbon and hydrogen atoms. Gasoline is nonpolar, and when you spill gasoline on water, it floats on top of the water because it doesn't dissolve in the water. It's not soluble. And that, again, is because it's an organic compound. Now, again, there's exceptions to that, but we'll take a look at those as the course progresses. In terms of inorganic compounds, if you remember, inorganic compounds, ionic compounds, are usually made from a metal and a non-metal, and therefore they will break apart into their ions, or they will readily dissociate, rendering them what we call water soluble. So just based on water solubility, you can see that there's a big difference between organic compounds and inorganic compounds. This table here, table 10.1, is a comparison of the major properties of a typical organic and an inorganic compound. So butane versus sodium chloride. If you've ever used a Bic lighter, let's say, the liquid that you can see inside a Bic lighter, if you hold it up to a light source, to a light bulb, or to the sun, you can see some liquid in a lighter. That's butane. And of course, when you release the pressure valve on a cigarette lighter, of course, the butane becomes a gas when it's under atmospheric pressure instead of the pressure inside the lighter. But butane is an organic compound, okay, so organic compound butane, and we're comparing it to sodium chloride, right, NaCl, which is an inorganic compound. And you can see that the reason they've chosen these two compounds is because their molar masses are virtually identical. They're about 58 grams per mole, both of them, so 58 and 58.5, so close enough. And the types of bonding, the organic compound, again, is held together by covalent bonds. So here's the molecular formula for butane. It has 4 carbon atoms and 10 hydrogen atoms. All of those atoms are bound together by covalent bonds, whereas in the ionic compound, of course, you have sodium as a cation and chloride as the anion, and those are held together by ionic bonds, right? The positive and negative are attracted by that electrostatic force. And it says here the physical state at room temperature and atmospheric pressure. So at room temperature, butane is a gas. And again, if you've ever, tried to hold down the pressure valve on a lighter before, you know that butane becomes a gas, whereas sodium chloride is a solid. And that is related to the intermolecular forces, right? We said that the intermolecular forces that hold organic compounds together are much weaker, and that's why it escapes, or it becomes a gas much more readily at room temperature and atmospheric pressure compared to sodium chloride, which is held together by those strong electrostatic forces of the cation and the anion. Boiling points and melting points, I'll go over this a little bit quicker, but you can see that the ionic compound, the inorganic compound, has a high boiling point and a high melting point, whereas the organic compound has a low melting point and a low boiling point. And again, that is related to intermolecular forces. The solubility in water, we discussed this on the last slide. The organic compound is made exclusively of carbon and hydrogen. Therefore, all of the bonds are nonpolar, and it is not going to be soluble in water, which is a polar compound, right? You remember like dissolves like. And you can see that sodium chloride has a high solubility in water, and the reason why is because it is an electrolyte. It will dissociate into a cation and an anion, which will dissolve in water. Solubility in organic solvents, again, following the like dissolves like, you see that the solubility for butane in an organic solvent like hexane, and we'll discuss what hexane is later on, you can see that its solubility is high, whereas the inorganics compound's solubility is low, insoluble. Again, that's like dissolves like. So hexane is a hydrocarbon and butane is a hydrocarbon, and that is why the butane will be soluble in hexane. Flammability, organic compounds, generally speaking, are flammable, and inorganic compounds are non-flammable. And then, of course, in terms of electrical conductivity, since an inorganic compound like sodium chloride is an electrolyte, it will conduct electricity in solution. And the organic compound, since it's a non-electrolyte, will be a non-conductor. So kind of a nice comparison of an organic compound and an inorganic compound of similar molar mass. As I said before, a class of organic compounds known as hydrocarbons contain only carbon and hydrogen. So it's kind of in the name here, you see carbon and hydrogen, so hydrocarbons. And they are non-polar molecules. It's important that you memorize this, that hydrocarbons are non-polar molecules. And the reason why is because all of the bonds in hydrocarbons are non-polar. And since water is a polar compound, since water is a polar compound, it stands to reason that hydrocarbons will not be soluble in water because they do not follow the rule, or they do not adhere to the rule like dissolves like. You're going to see that hydrocarbons are soluble in typical nonpolar organic solvents like toluene and pentane. And I'll just put here, toluene and pentane are both hydrocarbons. Hydrocarbons. And again, we're going to follow the rule like dissolves like. So if toluene and pentane, and we'll look at the structures of these later on, if toluene and pentane are hydrocarbons, that means that a hydrocarbon is going to dissolve in them, right? Because like dissolves like. Now looking at hydrocarbons in even more detail, and again, hydrocarbons are compounds that contain only carbon and hydrogen, no other elements. We can have what are called substituted hydrocarbons. So it says here that hydrocarbons are constructed of chains or rings of carbon atoms with sufficient hydrogen atoms to fulfill a carbon's need for 4 bonds. So this is one of the mantras of organic chemistry, is that carbon always forms 4 bonds. And a substituted hydrocarbon is one in which one or more of the hydrogen atoms is replaced by another atom or a group of atoms. So we're going to take a look at some examples of that. Now we can divide up hydrocarbons further into a family of hydrocarbons. So if you look at the top here, it says hydrocarbons, and then it kind of divides up into 2 main categories. If you look over here on the far right, we have what are called aromatic compounds, and those are cyclic compounds that can also contain double bonds. And those are something that we're going to look at a little bit later, but we can also have what are called aliphatic hydrocarbons. And aliphatic hydrocarbons can be further subdivided into 4 different classes. So we can have what are called alkanes, cycloalkanes, alkenes, and alkynes. Now in this chapter, we're mostly going to focus our attention on alkanes and cycloalkanes. And it says here that alkanes contain only single bonds. For example, ethane. Now the generic formula for an alkane is CnH2n plus 2. So in ethane, you can see we have a total of 2 carbons, and we have a total of 6 hydrogens. So if you think about that, if I have C2, 2 times 2 plus 2, so 2 times 2 is 4, plus 2 gives me 6, so that's C2H6. And if you count up all the carbons and hydrogens in ethane, you have C2H6. So that's the generic formula for an alkane, and again, we only have single bonds. Cycloalkanes, it says, are alkanes with carbon atoms bonded in rings. So cyclo, right? Cyclo in a ring kind of makes sense, kind of draw a connection there. So here we have 4 carbon atoms connected in a ring. Earlier on in this video, I showed you a compound where we had 5 carbon atoms in a ring, and we can have 6 or 7, and we'll look at many examples of that. If we have a hydrocarbon that has a double bond between 2 carbon atoms, like is shown here in this molecule that's called ethene, we call those alkenes. And if we have a triple bond between 2 carbon atoms, like we see in this molecule right here that we call ethyne, that class of compounds, or that family of compounds, we call alkynes. So again, this slide just kind of shows you how we can divide up the hydrocarbons into aliphatic hydrocarbons, hydrocarbons, and then aliphatic hydrocarbons can be divided up into alkanes, cycloalkanes, which is mainly the focus of this video, and then alkenes and alkynes. Now, in terms of hydrocarbon saturation, it says here that alkanes are compounds that contain only carbon-carbon and carbon-hydrogen single bonds. So you must remember this, or must memorize that alkanes only have single bonds. And the only kinds of single bonds we're going to see are carbon-carbon single bonds like this, or carbon-hydrogen single bonds. Nothing else. A saturated hydrocarbon has no double or triple bonds. Whereas alkenes and alkynes, we call those unsaturated because they do not have the maximum possible amount of hydrogens per carbon atoms. And an easier way to recognize an alkene or alkyne is that an alkene contains at least one double bond, and an alkyne will contain at least one triple bond. So here, the first example shows a saturated hydrocarbon, all single bonds. So if you follow the generic formula CnH2n plus 2, you can see that we have 1, 2, 3 carbons. So if I have C3, I should have H, let's see, 2 times N. So 2 times 3 gives me 6, plus 2 is 8. So C3H8. And if you look in this molecule, you see that we have 3 carbons and 8 hydrogens. Whereas in this unsaturated carbon, we have a double bond, and we do not have 8 hydrogens, even though we do have 1, 2, 3 carbons. Some hydrocarbons are cyclic and form a closed ring. So cyclic, forming a ring, right? We can have what we call aromatic hydrocarbons, and we can also have cycloalkanes. And this slide shows one example of each. Benzene is an aromatic compound, okay? So it's got a ring, but it also has double bonds in it. So you can see we have 1, 2, 3 double bonds. It's still a hydrocarbon though, because it only contains hydrogen and carbon. And the molecular formula of benzene, you can see, is C6H6. Cyclohexane, which is shown here, okay, this whole big molecule here, this is a cycloalkane. And it has 6 carbons, but it has double the amount of hydrogens as benzene. It's C6H12. And you can see that there are no double bonds in the cycloalkane. And the generic formula for a cycloalkane is CnH2n. And you might be wondering, well, I thought you said that an alkane had 2n plus 2 hydrogens. Well, when you have the cycle or the ring, it causes you to lose 2 hydrogens. So if we back up, the generic formula for a cycloalkane will be CnH2n, and the generic formula for an alkane will be CnH2n plus 2.